Ever get that feeling? Where you're just wading through tons of information, articles, studies, whatever, just hoping to hit that key insight without getting totally bogged down in all the details.
Yeah, information overload is real.
Exactly. And that's really why we started the deep dive. We do the sifting for you, pull out the really valuable stuff.
Kind of like a shortcut to the good parts.
Think of it that way, yeah. You're fast-tracked to being well-informed, maybe with a few surprises to keep it interesting.
Sounds good.
And speaking directly to you, our listener, we've really crafted this deep dive with you in mind.
Right.
We know you want to absorb knowledge quickly, but also thoroughly. You appreciate seeing different angles, getting those aha moments.
Without the headache of sorting through everything yourself.
Precisely.
Yeah.
No drowning in data.
Okay.
So let's get started.
Okay.
Today, we're diving deep into structural equation modeling.
SEM, yep. A big one in many fields.
And our main source here is the book Structural Equation Modeling, Applications Using Mplus by Wang and Wang.
Yes, Wang and Wang. A pretty comprehensive text.
It is. It's definitely an academic work, focuses on S and using the Mplus software specifically.
So not exactly beach reading.
No, not light reading. But it's absolutely packed with powerful knowledge.
Definitely.
Our mission today, to pull out the core ideas, maybe some surprising bits, the practical side of SEM.
And make it accessible.
Exactly. Make it understandable, maybe even interesting, no matter your stats background.
A worthy goal.
And to help guide us through this, well, sometimes complex terrain, we have our expert, someone who's great at boiling down complex stuff and giving it context.
Happy to be here and try.
Okay, let's unpack this. What fundamentally is structural equation modeling?
Okay, so at its heart, SIS is a statistical approach, right? It's for looking at relationships. Specifically, relationships between things we can directly measure, our observed variables.
Like answers on a survey.
Exactly. And the underlying concepts, the things we can't directly measure, we call those latent variables or factors.
Okay, latent variables, hidden concepts.
Right. Think of it like this. You have a bunch of slightly blurry photos of, say, a person. Each photo is an observed variable. Maybe one question about mood, another about energy level. SEM helps you piece those blurry images together to understand the clearer picture. They all represent maybe the latent variable of well-being.
Ah, I see. So it's building a clearer picture from fuzzy data points.
Precisely. And it goes further than just saying, oh, these things are correlated.
How so?
Well, SE allows us to actually propose and then test specific pathways. We can hypothesize maybe that one underlying concept influences another, or test if our chosen questions are actually good indicators of that hidden concept.
Okay, so we're moving beyond just correlation towards testing potential.
Yeah.
Well, not direct causation maybe, but pathways of influence.
Exactly. Testing hypothesized relationships in a more structured way. It's
Great.
definitely more insightful.
That sounds powerful. And you mentioned latent variables again. They seem really central here.
Oh, absolutely central. These latent variables or factors are the theoretical ideas we really care about. Things like anxiety, intelligence, customer satisfaction.
Things you can't just measure with one question.
Right. You can't just ask how satisfied are you and get a perfect score. Instead, we infer these concepts from a set of observed indicators.
So multiple questions point towards the same underlying thing.
Exactly. For anxiety, you might ask about worry, restlessness, maybe physical symptoms. Those are the indicators, and we theorize they reflect the latent variable anxiety.
Okay. But if you can't directly measure them, how do they get a scale? Like units of measurement?
Great question. Since they're unobserved, they don't have an inherent scale. So a common practice in SEM is to set the scale. We often do this by fixing the factor loading of one of the indicator variables to a specific value, usually 1.0.
Factor loading, what's that, roughly?
Think of it as how strongly that specific question, that indicator, reflect the underlying latent variable. By fixing one loading to 1, we're basically saying, okay, the unit of this latent variable is going to be based on the scale of this indicator. Ah, okay. It anchors the scale. It anchors it. And crucially, we almost always use multiple indicators for each latent variable. Wang and Wang really stress this.
Why is that so important?
Well, just like looking at something from different angles gives you a better 3D sense of it, using multiple indicators helps capture the complexity of the latent concept more fully. Different questions tap into different facets.
It makes sense, like using multiple sensors for a more reliable reading of temperature or something.
Exactly, that kind of idea. More reliable, more complete.
Okay. Now, the outline mentioned a measurement model and confirmatory factor analysis, CFA. How does CFA fit in?
Right, the measurement model. often using CFA. This is a really critical first step in DM.
First step.
Often, yes. Its main job is to check or confirm whether our chosen indicators actually measure the latent variables we think they measure.
So checking if our measurement tools are working properly.
Precisely. Are our blurry pictures really representing the clearer scene we intended? That's what the measurement model tests.
And how is this CFA different from, say, exploratory factor analysis, EFA?
Good distinction. EFA is more, well, exploratory. You put data in and see what underlying factors seem to emerge. You don't start with a strong theory about the structure.
Kind of letting the data speak first.
Right.
Yeah.
CFA, on the other hand, is theory-driven. You start with a hypothesis. I believe these specific indicators measure this latent variable, and those other indicators measure that one. Then you use CFA to test if your data actually fits that pre-specified structure.
So you're confirming a theory, not exploring for one.
Exactly. And Wang point out key differences in how you set up the models, like specifying which indicators should relate to certain factors or whether measurement errors might be correlated. It's much more constrained by your theory.
Okay. And within CFA, there's this idea of model identification. Sounds important.
Very important. Think of it like algebra. If you have one equation, like x plus y equals 10, but two unknowns, x and y, you can't find a single unique solution, right?
Right. Infinite possibility.
Model identification in SEM is similar. It means, do we have enough information in our observed data, our knowns, to actually get unique, stable estimates for all the things we're trying to figure out in our model, the unknowns?
Like the factor loadings, the variances.
Exactly, all those parameters. Wang use a simple example. If you only know the total variance of a score, VOR, you can't uniquely separate the variance due to the true underlying concept VOR from the variance due to measurement error.
Because VAR plus VOR equals VOR, and lots of combinations work.
Precisely. The model's unidentified. You need enough pieces of data relative to the number of things to estimate.
Okay, so assuming our model is identified, how do we know if it's any good? If it actually fits our data?
That's where model fit indices come in. These are like report card scores for your model. They tell you how well your hypothesized model, your statistical story, matches the reality found in your data.
And there are several of these.
Oh yeah, quite a few. Because they look at fit from slightly different perspectives. You'll see things like the chi-square test, CFI, TLI, SRMR, RMSEA.
Whoa, alphabet soup.
It can seem like it.
Yeah.
But they each give useful information. Wang mentioned some common rules of thumb, like maybe wanting an SRMR below 0.08 or CFI and TLI above 0.95, suggesting a good fit. But these are just guidelines.
Right. Not hard rules.
Definitely not. We also use things called information criteria, AIC, BIC, and others. They help compare different models, even ones that aren't directly nested. Lower values generally mean a better balance between fit and simplicity.
Okay, balancing accuracy and complexity.
Exactly. And finally, if the fit isn't great initially, you might look at modification indices. These suggest changes like adding a path that could improve fit, but, and this is crucial, Wang stress it, any modification must make theoretical sense. You don't just chase good fit numbers blindly.
Right. Theory has to guide the changes.
Always.
Okay, that's a really helpful overview of the measurement side, making sure our instruments are sound. Now, what about the structural model?
Right, so once you're reasonably confident in your measurement model, how your variables are measured, the structural model is where you specify the relationships, the paths, between the latent variables themselves.
So this is where we test how the underlying concepts influence each other.
Exactly. This is where you formally test those hypotheses about influence or potential causal links between your factors. Like, does work stress predict burnout? The structural model defines that proposed link.
And the book focuses mostly on recursive models.
Yeah, Wang primarily cover recursive models. That just means the influence flows in one direction, generally. No complex feedback loops where A affects B and B loops back to affect A simultaneously. Those are non-recursive, a bit more complex.
Okay. And can we bring in other observed variables here?
Absolutely. We often include observed variables as covariates. These are things we think might influence the latent variables.
Like demographics, age, gender, education.
Yep, exactly. You might hypothesize that age influences job satisfaction, so you'd include age as a covariate predicting the job satisfaction latent variable.
Got it. And the book mentions MI models.
Briefly, yes. MII stands for multiple indicators, multiple causes. It's a specific type of model where you have indicators measuring a latent variable, the MI part, and covariates predicting that latent variable, the MC part. They're useful for looking at covariate effects and also for testing measurement invariance, which we might get to.
Okay, so the structural model is really the hypothesis testing part for the relationships between our core concepts.
That's a good way to put it.
Now, a basic fact of life is that measurement isn't perfect. How does SEM handle measurement error?
That's one of SIM's biggest strengths, actually. Unlike simpler methods that often assume perfect measurement, SEM explicitly acknowledges that our observed variables have error.
Right, they're noisy.
They are. And SEM allows you to model that noise, that measurement error, directly. By accounting for it, you can get more accurate, less biased estimates of the true relationships between the latent variables.
Because you're filtering out some of the measurement static.
Kinda, yeah. You're statistically controlling for the unreliability of your measures. Wang and Wang even note that if you only have a single indicator for a concept, which isn't ideal but sometimes happens, you can use external information like a published reliability estimate for that measure to help fix the error variance in your model.
That's clever. Okay, so accounting for error gives us a clearer view of the underlying relationships.
Definitely a major advantage.
All right, let's shift gears a bit to some of the more advanced techniques, these intriguing nuggets, as the outline calls them. First up, Bayesian SEM or BSM. What's different there?
Okay, Bayesian SEM. It offers some really interesting advantages over the, let's say, classical or frequentist SEM most people start with. One big plus is flexibility with complex models.
How so?
Well, remember how in CFA we often fix certain paths, like cross-loadings, to be exactly zero?
Yeah, assuming an indicator only measures one factor.
Right. In BSM, instead of fixing it to zero, you can use what's called an informative prior distribution. This lets you say, okay, I think this relationship is probably very small, close to zero, but maybe not exactly zero. Allows for a bit more nuance.
More realistic, maybe.
Potentially, yes.
Uh-huh.
Also, BSM Mplus is what's called a full information estimator when dealing with missing data, assuming it's missing at random. Uses all available data very efficiently.
Better handling of missing values.
Yes, and it naturally incorporates the uncertainty around those imputed missing values. Plus, BSM handles mixtures of continuous and categorical outcomes easily, and it can help avoid certain technical problems, like getting impossible negative variance estimates.
By using those priors.
Exactly, by setting sensible prior beliefs. Wang and Wang point out it also opens the door to newer models like dynamic SEM, DSM, for intensive longitudinal data.
Sounds powerful. Any downsides?
The main thing is that choosing appropriate priors, those initial beliefs, requires some skill and understanding. It's not automatic.
Okay, more flexibility, handles complexity, but needs more user expertise. Got it. Next, item response theory, IRT. How does that connect?
IRT. Okay, so IRT is another framework for analyzing test or survey data, but it focuses very specifically on the characteristics of individual items or questions, especially when they're binary, yes, no, or ordinal, like a rating scale.
What kinds of characters?
Things like item difficulty, how much of the underlying trait someone needs to endorse the item, item discrimination, how well the item separates people with low versus high levels of the trait, and sometimes a guessing parameter for multiple choice.
Okay, focusing on the item level, how does that relate to CFA?
The connection is actually very close, especially when you do CFA with categorical indicators. The math underlying them is deeply related.
Really?
Yes. In fact, you can often mathematically transform the parameters you get from a CFA model with categorical items, the factor loadings and thresholds, directly into IRT parameters like discrimination and difficulty. Wang and Wang show how this works.
So they're kind of two sides of the same coin, in a way.
In many cases, yes, looking at similar information from slightly different perspectives. They also mention graded response models, which are IRT models specifically for items with multiple ordered categories, like Likert scales.
Interesting. So knowledge from one can inform the other. Okay, let's talk about comparing groups. Multigroup modeling.
Right. Multigroup SM is incredibly useful.
Mm-hmm.
It lets you test whether your entire SM model, both the measurement parts and the structural parts, works the same way across different populations.
Like comparing men and women, or different cultural groups, or maybe a treatment versus control group.
Exactly. Any distinct groups you want to compare, you can ask, are the relationships between variables the same? Are the average levels of the latent variables different?
But I imagine there's a catch. You have to be sure you're measuring the same thing in each group first. Right?
Absolutely critical. That's the concept of measurement invariance or measurement equivalence. Before you can meaningfully compare, say, average anxiety levels between two groups, you need evidence that your anxiety measure is functioning equivalently in both groups.
Like the ruler analogy again? Make sure the inches mean the same thing everywhere.
Perfect analogy. Wang and Wang discuss testing different levels of invariance. First, is the basic factor structure the same? Configural invariance. Then, are the factor loadings the same? Metric invariance. Can we compare latent means? Scalar invariance. Establishing these steps is crucial for valid group comparisons.
And this applies to change over time, too.
Yes, they briefly mention multi-group latent growth models, which let you compare growth trajectories like rates of learning across different groups.
Okay, check the measurement consistency before comparing the groups. Makes total sense. Next, latent growth modeling, LGM. Sounds like it's all about change.
Exactly. LGM is specifically designed for longitudinal data when you measure the same people repeatedly over time.
Like tracking student progress over several years.
Perfect example. The core idea is to model individual change trajectories using latent variables. Typically, you estimate a latent intercept factor where people start and a latent slope factor, their rate of change.
So you model both the starting point and the growth rate as hidden variables.
Precisely. And it's flexible. You can model linear change or nonlinear change using polynomial terms or piecewise models if growth accelerates or levels off.
What if the time points aren't evenly spaced?
LGM handles that well. You can specify the exact time scores. Wang and Wang even mention models where the time scores themselves can be estimated from the data, letting the growth pattern emerge more freely.
Wow, okay. And then they mentioned dynamic SEM, DS.
Yeah, DSM is sort of an extension for intensive longitudinal data, where you have many time points, maybe from daily diaries or sensors. It combines ideas from a time series analysis and SEM to model fluctuations in dynamics over time. Very cutting edge.
So LGM gives us a powerful lens on individual change. Very cool. Okay, how about mixture modeling, finding hidden groups?
That's the gist of it, yes. Mixture modeling aims to identify unobserved subgroups, latent classes, or profiles within your overall sample. The idea is that your population might not be homogeneous. It might be a mix of distinct types of people.
Based on their patterns of answers.
Exactly. Based on their patterns of responses across a set of variables. If you have categorical indicators, it's often called Latent Class Analysis, LCA. If you have continuous indicators, it's often latent profile analysis, LPA.
And how is this different from just, say, cluster analysis?
Wang and Wang emphasize that LCA and LPA are model-based. They have a stronger statistical foundation, providing fit statistics and probabilities of class membership, unlike some traditional clustering methods.
More statistically rigorous.
Generally, yes. And you can extend these ideas. You can see how covariates predict class membership or how class membership predicts later outcomes. You can do longitudinal LCA or latent transition analysis, LTA, to see how people move between classes over time.
People change groups?
Potentially, yes. LTA models that. And growth mixture modeling, GMM, combines LGM and mixture modeling. It looks for subgroups that have distinct growth trajectories.
So different patterns of change for different hidden groups.
Exactly. And they also briefly mention mixture factor analysis and mixture SM, which integrates factor models within this mixture framework. Super powerful for uncovering hidden heterogeneity.
It definitely sounds like it reveals complexity we might otherwise miss. Okay, one last technical point. Sample size. Always a big question. What's the advice?
Sample size for a sec. That's
kind of
complicated. As Wang and Wang stress, there's no single magic number.
No simple rule like you need 200 people.
Unfortunately, no. It really depends on many things.
Yeah.
How complex is your model? How many indicators per factor? How reliable are they? Is your data normally distributed? How much missing data? What estimation method are you using?
Okay, lots of factors.
Lots. So relying on simple rules of thumb can be risky. Wang and Wang point towards more sophisticated model-specific approaches.
Like what?
Things like the Sator-Saris method, or running Monte Carlo simulations where you simulate data based on your expected model and see what sample size gives you enough power, or methods based on achieving a certain level of model fit.
So you tailor the sample size estimation to your specific study?
That's the ideal, yes.
Yeah.
Get an estimate based on your model and your research context. They even mention a specific approach for latent class analysis. The bottom line is, think carefully. Don't just grab a generic number.
Good advice. Okay, before we wrap up, the source book heavily features Mplus software. Tell us about that.
Yes, the book is very much centered on Mplus applications. Wang and Wang really showcase its flexibility. It can handle all sorts of data, continuous categorical combinations, and latent variables that are themselves categorical.
It's versatile.
Very. And it excels at handling complexities that challenge other software. non-normal data, complex survey designs with weighting and clustering, multigroup analysis, sophisticated missing data handling.
And the advanced models we discussed.
Absolutely. It implements Bayesian CEM, dynamic CEM, mixture models, complex multi-level models. It's positioned in the book as a really powerful, comprehensive tool for pretty much the full range of modern CEM analyses.
Good to know. All right, this has been incredibly insightful, a real deep dive into CEM. Let's try to quickly recap the big takeaways. We've seen CEM's power in understanding complex relationships, going beyond correlation to test pathways between observed variables and those crucial latent concepts.
Right, the hidden variables.
We stressed the importance of the measurement model, CFA, making sure our tools are valid before we build the structural relationships.
Foundation.
We talked about how the structural model maps those relationships and, importantly, how CEM accounts for measurement error, giving clearer results.
Yeah, accounting for noise.
And then we touched on a whole suite of advanced techniques, the flexibility of BS, the item-level insights from IRT, comparing groups with multi-group models, tracking change with LGM, uncovering hidden subgroups with mixture modeling.
A lot of powerful tools in the CEM toolbox.
Definitely. Plus the practicalities of sample size and the capabilities of software like Mplus.
Covers a lot of ground.
So for you listening in, what really clicked? Did any of this spark an idea, a connection to something you're working on or curious about?
Hopefully some aha moments occurred.
We hope so. If you are intrigued, maybe pick one of these areas, LGM, mixture models, whatever caught your ear, and explore it further.
And the Wang and Wang book is a great resource for going deeper. Lots of examples.
Absolutely. Check out the book for the detailed info.
Mm.
Finally, just a thought to leave you with. We deal with unobservable factors all the time, right? Stress, satisfaction, motivation, market sentiment.
Everywhere.
So considering that, how might a better grasp of CEM, even just the core ideas, help us all make maybe more informed decisions or draw more accurate conclusions in whatever field we're in?
It's a powerful way of thinking about complex systems.
Something to mull over. Thank you for joining us on this deep dive.
Thanks for having me.
Until our next exploration, keep asking those questions.